is try to build on what Mr. Peresky did in talking about criticality. Start by talking about criticality in the context of a reactor, which is a static device. Talk a little bit about the physics of neutron multiplication, and then just get to the point of talking, leading us on the doorstep of what happens if you try to develop a supercritical assembly, and what are the things that matter when you try to design as this ensemble of the best experimentalists and theorists in the world, all gathered up in the Mesa in northern New Mexico in 1942, with the basic data in hand and really trying to conceive the best pathway to making a supercritical assembly that would be a bomb. So I want to build a little bit on that. Next week, I will wrap it up and talk more about where actually Dr. Hingorani last week did not get to, which is actually to talk in a little bit of detail, not too much detail, about what are the systems, depending on how you count 8 or 11 different systems in the US stockpile, where we may be going in the future, and so forth. And as I mentioned, I'm going to keep my toes very far behind the dotted line in talking about advanced topics like boosting and two-stage weapons, except in very, very general terms. But anyway, let me rip through this so you can get to your group meetings or otherwise. Anyway, we talked about, and you've actually done some exercises, and I hope you're developing some intuition about how one measures, and this is what the first experimental nuclear physicists did. In fact, they had to measure a lot of cross sections up to at the time of the Manhattan Project there. We developed the intuition that an experiment that measures a cross-section is one that where you put up a thin absorber, you have a beam impinging on it, and if you know the areal density, the number per square centimeter of scattering centers, and you measure the beam unattenuated downstream compared to the beam upstream, you can divide out the areal density and derive the quantity that contains the physics, which is called the cross-section. And of course, the cross-section, many things can happen when a neutron interacts with a nucleus. It can be absorbed, it can scatter, it might cause a fission, it might inelastically scatter, it might elastically scatter. One thing we didn't talk about, this should, I think, you should develop a little bit of facility for thinking about these things, just in the same way that if you have a large population of, for example, excited nuclei that undergo radioactive decay, in any given short time interval, you have a certain fraction that decay. Then you say, how many are left after 2 interviews? Well, if after 1 second, 80% survive, then after 2 seconds, 0.8 squared or 0.64 survive. After 3 seconds and so forth, it goes on and on and on. The same is true if I pass a beam through a thicker slab, a thick piece of matter. I can mentally divide a thick chunk of matter into thin slices, and if passing through the first thin slice of, for example, delta X, I attenuate 20% of the beam, the ones that are unattenuated stand an 80% chance of surviving, but a 20% chance of getting knocked out of play. You're down to 0.8 squared or 64%, et cetera, et cetera, et cetera. So going through a thicker slab of matter, you have exactly the same thing as in time, the exponential decay in time. You have an exponential decay in distance, where the number who survive after a significant thickness is going to be the initial number, n sub 0, e to the minus mu x. And just to cut to the chase, mu, which has dimensions of inverse centimeters, because when I multiply it by a thickness, I want a pure number in the exponent of the exponential. is the number density times the cross-section squared, like that. Okay. We've talked before about the two isotopes of interest for a weapon. These are both odd A nuclei, uranium-235 and plutonium-239. Each of them can absorb a neutron, in one case becoming uranium-236, in the other case plutonium-240. One is above the fission barrier. It'll immediately fission, give off more neutrons, and away you go. You have the possibility of a chain reaction. And what we're going to do today is talk about, by the way, just to back up a little second, the majority component of uranium is uranium-238, 99.3%. That will not fission normally unless you smack it very hard. And there you have to smack it above some few MeV of energy, and then it might or might not fission at that point. But it will not fission just by the absorption of a thermal neutron drifting in with zero energy, because when it absorbs it, it will gamma decay. It's not above the fission barrier. So let me do a bit of review of what Mr. Bresky did about 3 or 4 weeks ago here. Let's first talk about the context of a reactor. The way most reactors work in the world, essentially all power reactors, work on the fission of uranium, which is enriched to some interesting level. It might be 3 or 5%, or it might be 20%, 19%. But I think most power reactors are low enriched uranium. Every fission event will create neutrons. And the neutrons, you put these things in, these are light water reactors. You have the fuel inside of steel casing, and neutrons are emitted. You did a calculation, which you all turned in your homework at 5 p.m. Is this correct? Mr. Bresky has all your homework?
I was going to make an announcement later.
Okay.
Pretty good.
All right. You have calculated how many times a fast neutron, an MeV neutron, has to pinball around before it gets down to thermal energies. It's a surprisingly small number. It's quite amazing. You go from MeV down to 1/140th of an electron volt in a very finite, very small number of scatters. And the reason you do that, we've talked about before. Let me just show you a little bit. I found a little bit of a better picture here. In a real reactor, you have your fuel rods where the business end here, you get fissions, you get multiple neutrons. You have water where you undergo multiple scatterings to slow the neutron down. And then it can capture and then fission again, or it might capture and not fission again. And in this particular picture, you show that you actually have control rods here if you want to, as you must, continuously adjust the neutron multiplication factor K. And so in the case of a power reactor, you want something which puts out a constant power, like 3 gigawatts thermal, maybe 1 gigawatt of electricity. And if you ever want to change the power level, you do so over long periods of time in planned raising or lowering of the power level. But generally, you want to keep the thing exactly critical, K equals to 1, which means to say that on the balance, for every fissioning event, the neutrons will go out. There'll be several neutrons emitted. That on the average, each fission event will create 1, not more, 1, not less, additional fission event. So now we want to talk about, and by the way, here's the, power reactors sit here. Subcritical assemblies sit there. If K is greater than 1, we call it supercritical. If you really want to build a bomb, you want something where K is much, much, much greater than 1. Next time, we're going to go through the primer of what happens literally in less than a microsecond when you actually deliberately put together a supercritical assembly together, and how one actually goes about doing that, and how fast it all happens. Edward Teller actually invented a term which is actually a unit of time, which is called 10 to the minus 8 seconds. And in the nuclear weapons community, that's called a shake, one shake, just like you have a barn. And it was, Teller was saying that once you actually got basically a runaway chain reaction, everything happens in 2 shakes of a lamb's tail. So literally everything has happened. You can get like 80 generations of multiplication in a microsecond. So this was a convenient use of time, 10 nanoseconds, because things happen really, really, really fast once you put together a critical assembly. So let's talk about the life of a neutron, and it's really simple. What I'm really trying to do here is to actually get you to develop a little bit of intuition on what's important if you really wanted to design something that would to make a supercritical assembly, i.e. a bomb. And when you have a fission event, you say, haha, life is easy. I've got 2 or 3 neutrons coming out. I might have 1, sometimes I might have 4, and other times like that. But lots of things can happen to a neutron. It will scatter around, but it might get absorbed. Once in a blue moon, a neutron will attach to a proton, emit a gamma ray, form a deuterium. It's out of play. So what you have to do is think about what are all the things that can knock a neutron permanently out of play such that it doesn't cause another fission? Lots of things. It's like watching an Indiana Jones movies. You have to survive going through the cave. There are snakes. There's the crazy guy with a scimitar. There's all kinds of things. What's the probability he's alive at the end of the movie? Well, it's a product of probabilities that it survives the various caves and snakes and other assassins. So Mr. Koreski showed you the four-factor formula. And this was called K sub infinity. So first what I want you to think about is, think about a reactor that has fuel rods and water and other stuff which is not uranium. You have zirconium, you have steel, and so forth like that. But think of mentally, of course this never exists, but think mentally of the extent of the assembly being infinite in all directions. And so we're going to calculate K infinity, which is the neutron multiplication factor for this hypothetical or mental construct, which is a fuel assembly which is infinite in all directions. Now, it's a product of 4 factors. Let's see. Let's bring this down here. Sure. And the game is, for a power reactor, you want K infinity to turn out to be 1. And so you have 4 factors here. The first is the number of neutrons emitted per neutron captured in the fuel. And one of you quite astutely asked a question. They said, wait a minute. We always heard, you kept telling us, Van Bibber, that there are 2 or 3 neutrons on the average emitted per fission. Why is this number typically 1.9? And then, as Josh Rehak pointed out, where is Josh? He said, but remember, this is the number of neutrons emitted per neutron captured. Not every neutron captured by a uranium nucleus or plutonium nucleus causes fission. Some small fraction of the time, it'll capture gamma decay to the ground state, and once again, the neutron has been taken out of play. So this whole thing is thinking about what are the various ways that a neutron gets taken out of play such that it does not have the opportunity to cause another fission. So that's why this is less than the average number of neutrons, which is typically something like 2 to 3, depending on the conditions of the reactor and what your fuel is. Now, you have one good thing that can happen that helps you. When a neutron is first emitted, it's a fast neutron. Once in a very small fraction of the time, it can whack into another nucleus, whether it be 235 or 238, and cause a fission. So that actually gives you a little bit of help. It's typically a number that might be 1.03, so it's a few percent greater than 1. Everything else downstream of that is bad news, okay? You have neutrons, by the way. Let's talk about in all matter, as neutrons moderate and slow down, all of a sudden you go through a region where you see discrete states which have a very large capture cross-section. That basically means to say that in a certain band of energies, the neutrons are just going to get eaten up by anything. It might be iron, it might be water, it might be uranium itself. Give off a gamma ray and is taken out of play. So this factor is the probability is that it survives that, which is 1 minus the probability that it's lost. Fraction of neutrons surviving the resonant region. Let's just make up a number. It might be something on the order of 0.7. And then, even if a neutron is successful in slowing down, and you say, life is good, now it's going to find a uranium nucleus or a plutonium nucleus get eaten up and cause a fission, it can actually get gobbled up by the fuel or something else, and then not cause a fission. And when you look at all this thing plausibly comes out to something on the order of 1. And if you're actually running a reactor, the idea is to keep this thing exactly at 1. This is interesting if you actually looked at this Los Alamos primer, this document that Robert Serber, the little school he had in Los Alamos, the 2-week school for the new recruits of people literally your age or younger, you know, the cream of the crop of the best schools in the U.S., the Columbias and the Chicagos and the MITs and the University of Pennsylvania and Berkeley and places like that who got, went down going who knows why to who knows where in Los Alamos. They go up in get off in the train in Santa Fe and they make a 1-hour climb up in these old vintage automobiles up to 7,300 feet, and they get in this little log cabin, and they get a chalk talk on how they're going to build a nuclear bomb. This is what the world data was all about in terms of the fission cross-sections as they were known in 1942. And you look at modern measurements today, and by gosh, they're pretty darn good. They actually pretty much what you measure today, although they're quite a bit more primitive. The numbers were good enough. If you look up there, you actually see something very curious. They actually had a curious nomenclature. They called uranium-235, they called it 25, and plutonium-239, they called 49. The 2 standard for 92, which is Z, the number of protons. The 4 was plutonium, which is 94. And the last digit was 235 or 239. And then 238 is Z of 92. A of 238. And it's exactly what I told you. If you want to make uranium-238 fission, you actually have to smack the thing fairly hard. And it has a very low cross-section for fission. These things are not great either here, but if you can slow the neutron down to thermal energies, the cross-sections become like 1,000 times larger. That's how power reactors. Okay, so let's do the following thing. Let's actually look at this. So I think of this as water, and think of these as fuel rods. This is sort of a very schematized reactor. Okay, and inside here, well, you might have some steel or zirconium out here, and you might have your uranium in here, 238, 235. This is infinite extent. So what you see here is just a small piece of everything. All right, so let's look at the life of a neutron. Here's a fission event that produces 4 neutrons. You can see most of them do what you're supposed to do. They actually scatter from the protons in the water. They bounce around several times. Here's one that gets gobbled up. A neutron gets gobbled up by a proton, makes a deuterium, sends off a 2.2 MeV gamma ray. out of play. Here's one also that scatters, hits something in a fuel rod, but emits a gamma ray rather than fission. It's out of play. This one is successful. It scatters, you can scatter from IC nucleus, all of a sudden get captured by uranium-235 and fission, and then life goes on. This one, you don't know its fate, but you do know one thing, and that is whatever happens to it will be a nuclear process. And that's because this is an infinite assembly. So eventually it'll scatter and either ultimately get captured and emit a gamma ray, or if it's lucky, it will get captured by uranium-235 and fission. Here's the same picture, but this time, what you see is only what's on the white background. That is a finite assembly. So this is the edge of the assembly. Now, the picture can look roughly the same, except something else can happen. There's another loss mechanism for a neutron. The cattle can stray off the ranch. If the neutron happens to get to the edge of the assembly without being captured, goodbye, it's gone. So this one is a fast neutron that never scattered. It's gone. This one did a reasonable job of getting thermalized, but it also found its way to the boundary and said, goodbye, it's gone. So I can take what Mr. Poresky showed you and go to what's called in the business the six-factor formula. If you have a fuel of finite extent, it's just like before, except you have to count in the probability that it does not escape from when it's fast, or if it manages to get down below the resonance region. Oh shoot, this one is T. A slow neutron, thermalized, T for thermalized, the probability that the slow neutron does not escape the assembly either. Okay. You say, well, why do these nuclear engineers actually make this a product of two factors rather than they could have just one capital L, which is product of the two? The practitioners have their reasons. But the first thing you learn is the total mass is important. If the thing were bigger, the neutron, if it would escape beyond the boundary here, if the whole fuel assembly were bigger, in fact, it would have more opportunity to scatter and be captured and cause a fission out there. So total mass is important. Okay, what else is important? I'm going to take the same picture here, and what I'm going to do now is actually compress it. So question, show of hands. I now have the same total mass, same shape, but now I've compressed it. Is the probability that the neutron ultimately is captured and causes a fission, does it go up, does it go down, or does it stay the same? How many people say that if when I've compressed, taken the same shape, I've gone from, let's say, 1 meter on a side to ½ meter on a side, and now I have an initiating event of a fission here that shoots out several neutrons. Does the probability, or put it differently, does K go up, go down, or stay the same? How many people say K goes up? How many people say that K goes down? How many people say that it stays the same? Okay, let me put it to you this way. Imagine that I had a gun where I shoot a bullet and it just goes in a straight direction for forever and ever, or I shoot a laser beam. Suppose I have a small forest of trees, like 100 trees, and the first forest is like 100 meters by 100 meters, and I just randomly point the gun or the laser beam at some point, and I fire. there's a certain probability I'll hit a tree. Imagine that I now take the same forest, the same trees, but instead of being 100 meters on the side, they are 500 meters on the side. The forest is more sparse. I put a blindfold on, I point it in some direction and shoot. What's the probability that I hit a tree? Does it go up or go down? Down, yeah. It's really that level of intuition I want you to have. Not only is the total mass important, but the density is important. And this does get important when you get into nuclear weapons physics. Okay? The underlying thing going on is all the same, but, and by the way, you can see this because remember the mean free path, which we defined before, lambda, which is 1 over mu, goes like 1 over the density times the cross section. Okay? Yeah, so this thing has, and then the cross section has units of centimeters squared to the -1. If the density goes up, then in fact the mean free path goes down. So if I take something that is a meter on a side and I compress it down to half a meter on the side, the density has gone up by a factor of okay, 1 meter to half a meter on the side, same amount of matter. The density has gone up by a factor of 8. Yeah, factor of 2 cubed, right? The volume is only 1/8 as it was before. Now, the distance to the boundary has gone down by a factor of 2. So in fact, the probability that the neutron is going to hit something on its way to the boundary has gone up by a factor of 4. So okay, the square of the factor you compressed it. So not only is the mass important, but the density is important. There's another thing that's important. Suppose I took the same amount of material as here. Forget about compressing it. I took the same ordinary density matter, but in one case, it might be a nice shaped like a cube, or I might put the thing in a sphere of a certain radius. Suppose I took the same amount of mass and I reformed it into a large tube like that. Okay. Here's A, B, and C. A, B, and C all have the same volume. Okay. So now I've taken the same amount of matter. In fact, since it's the same amount of matter, you can't see the fact that it sticks out on either end. And I have a fission event in one of the nuclei in this large bar, like this, which has got a long aspect ratio. Does the neutron multiplication factor go up, down, or stay the same? How many people say it goes up? How many people say it stays the same? How many people say it goes down? Yes, why? It's really intuitive.
Surface area?
Yeah, it's all spin now. I mean, if you're a nucleus here, when you go pop, if you were in a very compact object, the only way out, you've got a very long path to get to the edge on the average. Here, given that the neutron can go in any particular direction, most of the time you're very close to getting to the fence. Okay, so the third thing that matters is mass, density, and shape. Shape is very important if you want to make a nuclear weapon. What's the most, well, just intuitively now, having said that, what's the best shape you'd like to have?
Sphere.
Sphere, ultimately. Yeah, intuitively that's right. I mean, the nuclei are going to go popping everywhere here. The ones that are near the edge, yeah, you're going to lose more neutrons over out the fence. But on the average, the sphere is the best shape that you'd like. So mass, density, sphere. I can play one more trick, which is played to great advantage in nuclear weapons, and even in the first. What's a trick you can play, given that we just talked about shape?
Amounts.
What?
amount of material?
That's total mass.
Okay, sorry.
Okay, so the cattle are escaping beyond out of the ranch. What do? Reflector. I can put in what is called a tamper. Actually, is getting a bit technical. Very often when you compress something explosively, to keep the thing from squishing out or whatever, you actually have a very heavy mass to give a lot of inertial push to push the thing in. You can also have that thing called a tamper double duty as a reflector. And a number of nuclei are very good as reflectors. Beryllium is very good as a reflector. So here's a neutron that was about to stray off the branch, but in fact reflected back in caused a fission. Having a reflector around a critical assembly can dramatically drop what's called the critical mass by large factors. Just a few centimeters of beryllium around this. Anyway, that's about all I wanted to say today. I'll let you guys work in groups. And I'm going to bring this to closure next time with a little bit of talking about, at the level of the Los Alamos primer, which is an unclassified document, we'll talk about the little boy, fat man, a little bit, very schematically, about modern nuclear weapons, what the stockpile is like, and so forth. And also we'll conclude with some things about where does the energy go in a nuclear explosion, and then the sort of the blast, radiation, heat, and ultimate biological effects as well. So there you go. Thank you.